First of all, should we be prepping?
We should monitor it. That's the way science is done. We shouldn't assume we know the answer about its nature in advance.
Right after perihelion at the end of October 2025, fresh images of the interstellar comet 3I Atlas revealed something dramatic. Narrow jets were spraying out from the coma, and a bright sunward spike known as an anti-tail stood out against the dim glow. For a visitor from another star, that pairing raises two urgent questions. What physics shapes those features, and how can our viewing angle trick the eye into seeing patterns that are really geometry at work, rather than new kinds of matter? This moment matters because 3I Atlas is only the third confirmed interstellar object ever studied in the solar system. The weeks after closest approach to the Sun are prime time for diagnosis. Sunlight has warmed the surface and shallow subsurface, fresh fractures can open, and newly lit vents can switch on as the nucleus rotates. In this phase, we can read the comet's behavior as if it were a slow-motion experiment in vacuum, watching how gas escapes, how dust is sorted by sunlight, and how magnetic fields and the solar wind sculpt the scene. The observing window is short. As the object recedes, it fades and the geometry changes. That makes every clear night valuable. In one line, here is what 3I Atlas is. It is a hyperbolic interstellar comet discovered by the Atlas survey in early July 2025, not bound to the Sun, and on a one-time pass through the inner solar system. It swung past the Sun around the 29th of October at a distance a little over 1.3 astronomical units. It is not a hazard to Earth, with minimum distance roughly 1.8 astronomical units. Early imagery from major facilities and a global pro-amateur network set the stage for a post-perihelion return, when the comet rose before dawn and slipped out of the Sun's glare. What did the new images show? Several teams captured a complex multi-jet pattern on nights around the 8th and 9th of November when the comet was low in the morning sky. Long stacked exposures revealed at least a few discrete narrow jets emerging from the inner coma, plus a long tail stretched away from the Sun. Most striking, some images displayed a sharp sunward feature that looked like a jet aimed back toward the Sun.
Well, what we see are 7 jets coming out of these objects.
The anti-tail. Reports placed the scene at a modest solar elongation, so the Sun was just off the frame, a setup known to emphasize thin features aligned with the line of sight. The morphology matched what comet watchers hoped to see as the object re-emerged. To understand the anti-tail, it helps to step back and recall the basic types of comet tails. Ion tails, made of gases blown by the solar wind, point roughly away from the Sun along magnetic field lines. Dust tails, made of tiny grains pushed by sunlight, also tend to stream anti-solar but with curved shapes because larger grains feel less force than smaller grains. An anti-tail looks like the opposite, a sunward spike. The key is geometry. When Earth passes near the plane of the comet's orbit, we look edge-on through a thin sheet of dust that the comet already released earlier in its path. Those grains are concentrated near the orbital plane, especially the larger ones that resist light pressure. The edge-on view stacks that dust along our line of sight and produces a bright, narrow structure that seems to point toward the Sun, even though the material is actually trailing along the orbit. In other words, the anti-tail is not fighting physics. It is an alignment effect that appears at certain viewing angles and then fades as the geometry changes. Now, what are jets? Jets are collimated outflows erupting from localized vents on the nucleus. Ice patches on or just beneath the surface sublimate when they rotate into sunlight. Gas escapes through cracks, pits, and porous layers, dragging dust with it. If the nucleus spins, the jet direction slowly sweeps, which can create fan shapes and spirals in time-stacked images. After perihelion, thermal lag means warmed layers can keep venting even as the comet starts moving away from the Sun. Hubble's early view in July showed a dense, dusty coma around 3I Atlas, which told us that sustained outgassing was already underway. With the Sun now out of the field and the geometry improving, the November sessions made it easier to resolve narrow features and map them to potential vents on the spinning nucleus. How big are these structures in space? Observers described the anti-tail and main tail spanning many arc minutes when the comet was hundreds of millions of kilometers from Earth. Even a 10 arc-minute feature at that distance implies a structure on the order of 1 million kilometers long. A larger span can reach several million kilometers. Those are orders of magnitude checks rather than precise measurements, but they match what similar geometry can produce in well-studied solar system comets. The key takeaway is that a pencil-thin spike on your screen can represent an enormous volume of dust grains, size sorted by physics and arranged by orbit dynamics. What do we know with high confidence, and what remains open? We know the timing of perihelion and the distance are well constrained by orbital dynamics. We know a multi-jet morphology appeared in early November as the comet came out of the glare. We know the minimum Earth distance remains comfortably large. We do not yet know the exact volatile mix driving the present jets. Water ice, carbon dioxide, and carbon monoxide can all dominate under different temperatures, and spectroscopic data with good signal-to-noise is needed to separate them. We also do not yet know how much of the brightness changes in the tails reflect real changes in activity versus pure viewing geometry. The Sun-Comet-Earth angle controls how a dust sheet brightens when viewed edge-on. Finally, we do not yet have a settled rotation state or a map of the active vents across the nucleus. That requires time series imaging across many nights to track repeating features and to solve for the spin axis. The right way to test explanations is to start with mainstream comet physics. The simplest model for the November scene is post-perihelion jetting from several discrete vents, plus an anti-tail created by orbital plane geometry. That combination is common when geometry cooperates. On a fast interstellar comet, the plane crossing happens on a different schedule than for a typical long-period comet, which can make the anti-tail appear especially sharp for a short window. Some voices have raised more exotic possibilities. It is healthy to ask hard questions, especially for interstellar visitors. But extraordinary claims need instrument-grade evidence. That means repeatable photometry, properly calibrated spectra, and astrometry that accounts for non-gravitational forces without overfitting. With the data in hand today, the conservative reading remains natural outgassing and projection effects. Occam's razor points there until better evidence arrives. Which instruments are doing the work, and what can they actually tell us? Hubble gave a high-resolution look at the coma in late July and helped constrain size and brightness in the discovery era. European Southern Observatory and European Space Agency assets anchored the hyperbolic orbit and tracked activity early on, and those networks often continue follow-up as geometry improves. A strong pro-amateur community, including organized comet observing programs and projects like the Virtual Telescope, is feeding a steady stream of images that capture morphology during these tricky low-altitude mornings. On the navigation side, NASA and community orbit tools keep ephemerides tight so observers can plan long integrations and narrowband filter work to separate gas jets from dust fans. Why is November tricky and still rewarding? The comet sits low before dawn, with the sun not far below the horizon. Haze, twilight, and moonlight can wash out diffuse features and make thin dust sheets seem relatively brighter. That can overemphasize an anti-tail while hiding a faint ion tail, unless long exposures and careful filtering are used. As solar elongation grows later in November, the separation between features should improve. That will make it easier to distinguish the fan of a rotating jet from a line-of-sight dust sheet, which in turn helps model the spin pole and locate the source regions that turn on and off. What can jet geometry reveal about the nucleus itself? Each jet's position angle on the sky maps back to a source latitude on the nucleus, once the spin axis and the viewing geometry are solved. If two or more jets recur at the same angles over several nights, they likely trace persistent vents tied to the body frame. If the angles drift, that could indicate precession or changing illumination as the comet moves along its path. The narrowness of the anti-tail hints that larger grains dominate in the sheet, since larger grains feel less radiation pressure and stay closer to the orbital plane. By comparing the gentle curvature of a jet with the comet's speed and with standard values for how strongly light pushes different grain sizes, observers can estimate a distribution of grain sizes. That is a direct clue to how ices cement dust in an interstellar nucleus, and how easily those grains break free. It is important to be cautious. Many early November frames were captured at very low altitude under a bright moon. Morphology is the robust result, but absolute brightness should be treated carefully until more calibrations are complete. Spectral composition remains an open question. The early Hubble view showed a dusty coma, but could not fix the volatile ratios. Mid-infrared and high-resolution near-infrared spectra would be ideal to separate signatures of water, carbon dioxide, and carbon monoxide now that the comet is cooling. Speculation about unusual or engineered origins should be kept separate from the current evidence. Natural cometary activity and projection geometry explain the observed features well, and that is where the weight of data points. Here is what to watch next. As November moves toward its end, the angle between the comet and the sun from Earth grows, improving contrast and helping separate jets, the dust tail and the anti-tail. That should enable narrowband imaging runs that pick out gas species and help link specific jets to specific volatiles. In December, when the comet is roughly 1.8 astronomical units from Earth, deeper time series should make it possible to solve for the rotation state and map the main vents with better confidence. Astrometry campaigns are already underway to refine the orbit solution using coordinated measurements. Any spectroscopic detection of unusual volatile ratios after perihelion would be a headline result, because composition is the fingerprint that ties this object to conditions around its unknown parent star. So, what is the measured takeaway? The post-perihelion images are exciting, but they do not require anything beyond comet physics and viewing geometry to understand. 3i Atlas is active. Multiple sunlit vents are sculpting narrow jets. The anti-tail is a line-of-sight enhancement from dust concentrated in the orbital plane that we happen to be viewing almost edge-on. For an interstellar visitor, this is exactly the kind of readable scene we wanted. It is a natural laboratory where morphology can be measured, geometry can be modeled, and composition can be probed as the data improve. As the weeks progress, expect cleaner separations of the features, more precise solutions for the spin axis and vent locations, and with luck, spectral fingerprints that tell us which ices are powering the show. Every step tightens our picture of how a small body from another star behaves under our sun, and every data run adds a piece to the growing map of what interstellar ices and dust look like when they finally meet the light. Right after perihelion at the end of October 2025, fresh images of the interstellar comet 3i Atlas revealed something dramatic.